Jai Hind everyone. I am Shraddha Mishra, Assistant Professor, Department of Information Technology, Ajay Kumar Garg, Engineering College. Today, we will be having a lecture on discrete structures and theory of logic. We will be discussing propositional logic today. So, let's start with the lecture. Propositional and predicate logic. So, what do you mean by logic? So every time we try to conduct certain activities and we say to our peers, what is the logic behind this you are doing? This is rational, this is irrational. So what do you understand by logic? Propositional logic and predicate logic. So before we start that, we have to understand what is logic. So logic by Oxford Dictionary means the systematic use of symbolic techniques and mathematical techniques to determine the forms of valid deductive argument. Thus, logic is the common language by which we can demonstrate the validity of our reasoning. So, logic simply means if we put the reason, we have certain facts and certain arguments to validate that, to back them up. So, that is logic. Here in mathematical form, it means you can express it in the form of mathematical equations and expressions. Now, propositions. What do you mean by a proposition? So, it's a declarative statement that's either true or false, but not both. Lucknow is the capital of Uttar Pradesh. So, this is 100% true. So, proposition means it's either true or false. It's black or white, but not grey. So, 9 is less than 4. So, this is wrong. So, this is absolutely false. Delhi's capital goods are absolutely false. It's not like a black or a white. It's a grey. Propositional logic is the branch of logic dealing with reasoning about propositions. So, if you talk about propositional logic, so it deals about reasoning of the propositions. That means if you are saying that a certain logic is true or a certain logic is false, so how do you back it up? What is the mathematical equation to prove that? Let P and Q be the proposition that P, all math students wear glasses. Q, all EE students know how to wire a plug. So, you can see now we can express it in the form of statements. Now, negation and use of propositions. So, Delhi is capital of India, Delhi is not capital of India. So, P we had used as a mathematical expression and not P is the other expression. So, we can express it. So, whatever we have learned in our English grammar schools that you know how we can negate statement, but how to express it in the mathematical form is what we will learn here. Logical connectives with precedence, bracket or, and this is a disjunction, conjunction, exclusive or, and these arrows. So, these are the precedents. Now, logic and bit operator. A bit is a binary digit 0 or 1. Bits are usually used to represent truth values. By convention, 0 represents false, 1 represents true. Bit operations corresponds to logical operators representing false by 0 and true by 1. We very well know 0 means false and 1 means true. Now, truth values of compound statements. So, for example, now this is very, very important. If I write here P and Q, because in exams the questions which come is, it is going to be an expression in the form of P and Q and you have to solve it. So, when you have to solve it, what do you understand is, if you know not, you know it is going to be absolute negation, you know this and, so you know and or. So, you know that either both are true, only then, or both are true, or if either plays 0, it is going to be false, right? Only if both are true, it's going to be 1. You know for the or that if either of it is 1, it is going to give 1. Now, this, you can see that either both, you can see here either it's a 0 and 1 or it's a 1 and 0. Only in that case, it's showing 1, right? So, you have to learn these tables respectively for being able to fill these, for able to expand your expression. You have to be very, very good with these. What does these mean? Once you have these in hand, you can very well express. So, as soon as I have in this expression as this P arrow Q, I very well know that if it is 0, 0, it is going to be 1. If it is 0, 1, it's going to be 1. If it is 1, 0, it's going to be 0, and if it is 1, 1, it's going to be 1. So, you see either it's, if it is both 0 or both 1, only then it is 1, 1, and also if the first is 1. if the second is 1, then also it is 1. So you can say only in the case when first is 1 and second is 0, it is 0. Rest every other case it is 1, right? And if you talk about double arrow, then in double arrow it is very simple, either both 0 or both 1, it is going to be 1. So if you see here, so either both 0 or both 1, it is 1, 1. And what about P arrow Q? If the first is 1 and the second is 0, it is going to be 0. Rest all cases it is 1. If you talk about this, similarly you can see if both are 1, it is 0. And here in the downward arrow, if both are 0, then it is 1. So once you have a good hand over this, we can expand the most difficult questions also. Now conjunction and disjunction. So we very well know this is the symbol of conjunction, which is and this is the symbol of disjunction, which is or. Implications. When we say P implies Q, written by this means P implies Q, we mean the proposition which is false when P is true and Q is false and otherwise true. When P implies Q, we might say if P, then Q. P is sufficient for Q, Q if P. Okay, let's understand with the help of an example, right? So this means P implies Q, means if P is true, only then Q apply, right? If Earth exists, only then we'll talk about life on Earth, right? So the first condition has to exist for the second to apply. Suppose P, I revised, Q, I passed the exam. Then P implies Q, if I revised, then I passed the exam, or I passed the exam if I revised. So I revised only if I passed the exam. Now, propositional equivalence. So what is tautology? These are very important expressions. They come in university exams for 2 marks. So what do you mean by tautology? Tautology is proposition which is always true. So whenever you are expanding an expression and you see that the end result, everything is true, you can say it's a tautology. Contradiction, if all are false. Contingency means it's a proposition that's neither a tautology nor a contradiction. So it's a mix. Sometimes it's false and true. It's a contingency. Now, logically equivalent. What do you understand by this? This is a symbol of logically equivalent. So if P and Q are propositions, then P is logically equivalent to Q if the truth tables are the same. So if we have the truth table same, then we say that they are logically equivalent. P, Q are logically equivalent if their biconditional is a tautology. Then we have this identity, right? P and you do the conjunction with P, you have this P domination. Idempotent is that same P union P, you have P itself. Double negation, negation ka negation is the number itself, right? Now commutativity. So if we talk about this, it's very obvious. P conjunction Q is equivalent to P disjunction Q is equivalent to Q disjunction P and so on. Similarly for associative, right? You can again open the bracket and distribute. Similarly for the distributive, P union Q disjunction R. Here is P disjunction Q conjunction P disjunction R. De Morgan's not P and Q is not P union not Q. That is De Morgan's law, right? So this union has changed here like this and this junction has close to this. So everything is equivalent to what we have read in set and function, just the symbol has changed. Now excluded middle, uniqueness and a useful LE involving. So this is very important thing which you have to know. Now P union not P is true, right? And uniqueness is P and not P will be false. Now if you have this P implies Q, so not P union Q, so very important. So just in case we have to expand the expression. So if it is P implies Q, it means not P union Q. So instead we can use based on our convenience. Now use known logical equivalence to prove that two propositions are logically equivalent. Now here we have this question which usually comes in exam and we have to prove. So usually we use truth tables. Now if you see here, negation ka negation is the number itself, right? Now Equivalence formulas. So these are the certain equivalence formulas. For instance, we discussed this. P implies Q, not P union Q, right? Similarly, negation ka negation is P. P union P is P. P and not P union Q is Q, because this itself is true, and anything a union with true is that number itself, right? So similarly, we have these properties, right? This is De Morgan law, P and Q, so not P union, not Q, right? And this is again a very, very important property, if you can see here. So it's really important. This P double implies Q, so this is P implies Q and Q implies P. Three close relative of the conditional statements: converse, inverse, contrapositive. This is really very, very important. It comes in 2 marks. Now, for example, this is a conditional statement, right? So what do you mean by its converse? Now, if we talk about a normal English, for us, they are synonymous to us, right? You have a true statement. I have to write the converse of it, inverse of it, contrapositive. For example, I say that it rained yesterday, and I could negate it. It didn't rain yesterday, right? Now, for us, it's in grammatical or in synonymous English, it means the same. But when we talk about propositional logic, means you have a logic. You are expressing it in the form of a expression, an equation. And now, in that expression, you have to write the converse, inverse, and contrapositive. Then there are different mathematical expression you have to make out of that. Then again, you have to, so from the word, you convert it into mathematical expression, and from mathematical expression, you again convert it into word. You can't directly, as in English, per se, you can't convert it. You really have to take one step extra, convert it into mathematical expression, which is like proper grammatically, and then you convert it into the normal English. So let's understand. For example, this is the expression P implies Q. Converse is, the converse of a given conditional statement is defined by interchanging the antecedent and the consequent. This is called antecedent, another is consequent. That is, the converse of P double implies Q is Q implies P. So converse is as a normal, in the layman language, you just swap it. So like instead of P we have Q, Q we have P. So that is the simple meaning of converse. Inverse, the inverse of a given conditional statement is defined by the negation of the original antecedent and consequent both. So inverse means you keep P and Q in place, just not is added to both the pieces. So inverse, right, means that you are in your place. As the name says, inverse, in your place. P, Q will be in their place, but you are versing it. Means you are putting negation to both of them. Contrapositive. The contrapositive of a given conditional statement is defined by the antecedent is a negation of the consequent, and consequent is a negation of the original antecedent. Contrapositive is the amalgamation of both of this, which says I will not just swap your places, but I will also put negation. So contrapositive means first they will swap the places and then they'll put negation. So converse simply means that you just swap the places. Inverse means you will be in place, we will just put a not. And contrapositive means you will not just swap but also put negation. I hope this is clear. Let's proceed. Argument. It's an assertion that a given set of proposition P1, P2 till Pn called premises yields has a consequence another proposition Q called the conclusion and is noted by P1, P2 till Pn. What's a valid argument? An argument P1, P2 till Pn, Q is said to be valid if Q is true whenever all the premises are true, right? So an argument is a valid argument if we say that all the premises are true. What is a fallacy? It's an argument which is not valid. Now P1, P2 till Pn, they are true simultaneously if and only if proposition P1, P2 till Pn is true. Hence we have the following theorem. What does the theorem says? The argument P1, P2 till Pn, Q is valid if and only if Q is true whenever P1, P2, P till Pn is true, and Q will be a tautology. Now procedure to prove the validity of an argument. The conclusion Q is said to be logically follow from the given premises if either of the following conditions is satisfied. So we can say that this conclusion Q is logically follow from these premises if either is satisfied. For example, if P1, P2 certain premises and their end result has to make Q true. So you might have a certain level of statements. They have to help you yield that final result Q. So how do we prove that? So there are two steps to it. Either you can do it Q is true whenever all the premises are simultaneously true, or Q is true whenever conjunction P1, P2 to Pn is true, or P1 intersection P2 so on, Q is a tautology. Procedure to prove the validity of an argument, you can check here. Alright, for example, this is a question, this has come in exam. To prove P implies Q, okay, so how will we prove it? We have simply taken 0, 0, 1, 1, 0, 1, 0, 1, right? We have taken these standard expression and we had to simply prove 0, 0 ka 0, 0, 1 ka 1, 1, 0, 1 because it's a union, right? 1, 1, 1. We all know this. So we can very well see that this is true whenever P is true. So whenever we had this 1, this was 1. So this is, you have just converted the words into the numerical form and proved it. Now here similarly, now this is quite important question which might be asked in AKTU because we do ask these kind of questions. Example, show that P double implies not Q does not logically imply P implies Q. So what we will try to figure out the elements we need. Now if you see this, you understand you need P, you need Q and you need not Q here, right? And what is this? So we have used this, right? And we have used this expression. So you can see that here it is 0, 0, here it is 1, okay. Now when you solve this double implies, we have read in the earlier table that when it is double implies means either both 0, then it is going to be 1, or either both 1, then it is going to be 1, right? So now we are discussing with not Q. So we will not see this table, we will see this table. So this is 0 here, where, okay, so this is 0 here and next where it is 0, 0. If you see here, 0 here, 0 here, so it is 1. Okay, if you see here, 1 here and 1 here, because you are talking about, see, double implies. Double implies means either both 0 or both 1, answer will be 1, right? Now here instead of Q, they have given not Q. So we will refer this table for P and not Q. Means in both of these tables, when do you have both 0 or both 1? So you see in these two cases, you have both 0 or both 1 and it is both 1 and then 0, right? We figured this out. Now, this here it is single implies. Single implies what was that? Means whenever first one is 1, in that case it is 0, rest all 1. So, we have done and we have proved. So, just have to expand. First order predicate logic. Now, but there are certain limitations. For example, there is a fact Peter is a man, Paul is a man, John is a man, can be symbolized by P, Q and R respectively in propositional logic. Can't draw any conclusion but similarity between P, Q and R. Because this is a man is common everywhere, right? So for this we might make P, Q, R, but what about this? These are all same. So we can't draw any conclusion. So it is better to represent these facts as man Peter, man Paul and man John. Even more difficult to represent sentences like all men are mortal in propositional logic. Such statements really need quantification, right? So there are certain limitations that, for example, if the conclusion or the second half of the statement is very common, then it's very difficult to draw a conclusion. Or if you use quantifiers like all men are mortal, so all, how do you quantify that and how do you express it in the form of a statement? So in these situations, there are drawback of predicate logic. So predicate logic is logical extension of propositional logic. First order predicate logic is one where the quantification is one simple variables. Now, if we see here, propositional logic is limited. Example, how do we express all maths undergrads are clever in terms of the cleverness of particular maths undergrads, or express there is a maths undergrad wearing sandals in terms of whether each individual maths undergrad is wearing sandals, right? So we therefore generalize the idea of a proposition to a predicate. Predicates takes one or more variables as arguments, and that is about predicate logic. Let's just understand with the help of an example. Let P Px be the statement x greater than 12, then P of 1 is false, P of 23 is true, right? So for the different values of x, the answer will vary accordingly, right? If you take x as 1, this is false. If you take x as 23, then this is true, right? That Px denote the statement x is a faculty of the MC department, then P Dheeraj is true, but P Akash is false, right? Maybe Dheeraj is a part of MC, but Akash is not, right? So it depends on the value of x. That is predicate logic. Universal quantifiers, those which refer to all the elements of a certain set. Existential qualifiers. Existential qualification is the proposition where there is an element x in the universe of discourse such that P of x is true. Propositional function. For example, Ax, x is a flower, Rx, x is red. So you express it like this in the form of a function. You draw a relation between them. Let's understand this third example. So there are three different expressions given to us. X is the father of the mother of Y. So we name a person called Z as the mother of Y. Now we want to say that X is the father of Z and Z is the mother of Y, which is symbolized as. So this is the relation we have drawn from these three statements. We have just put a not symbol here. Now, inference theory. So these are the 6 types of inference theory: law of detachment or modus ponens, law of contraposition or modus tollens, hypothetical syllogism, disjunctive syllogism, conjunctive dilemma, and destructive dilemma. Law of detachment, we can understand modus ponens. P implies Q and P will imply Q. So you can see here with these symbols, right, where we'll use it whenever we have to draw out of the premises, we have to draw a conclusion, we will use these theorems to prove that, right? So if Mohan can work hard, then he will get a job, and Mohan work hard, therefore he gets a job. So you can see the premise here is, so if you see your law of detachment, which is modus tollens, so you see here, modus ponens is your law of detachment. You see P, Mohan can work hard, Q, he will get a job. So we have expressed premises, P implies Q and P, and conclusion was Q. So you can see it in the form, right? So these are the certain examples we can practice on our own, right? Then we have the natural deductions. So thank you so much, everyone. So that's all for today. Hope you understood it. Now let's wait for our next lecture. Thank you so much.